Welcome to Agents of Tech, the podcast where we explore the groundbreaking innovations and critical ideas shaping our future. I'm Autria Godfrey here in Washington, D.C.
And I'm Stephen Horn in London. Today we'll be exploring how to meet AI's ever-increasing demand for data storage. As AI advances at breakneck speed, pushing traditional data infrastructure to its limits, AI not only needs large amounts of data for training, but also for greater data infrastructure for data storage and memory.
Steve, I don't know how closely you've been paying attention to what's going on across the pond over here, but we have been on an AI roller coaster. We have the Stargate Project that was just announced by the Trump administration, and it's a new company which intends to invest $500 billion, that's a capital B, over the next 4 years, building new AI infrastructure for OpenAI here in the United States.
Stargate will be building the physical and virtual infrastructure to power the next generation of advancements in AI, and tremendous amounts of money are coming in.
We're talking ARM, Microsoft, NVIDIA, Oracle, and OpenAI are all key initial technology partners. So truly everyone at the table is coming together here. Of course, they're going to be dealing with DeepSeek AI. That's a startup backed by a hedge fund, High Flyer Capital Management. And they've released a version of their AI chatbot, R1, that they say can perform just as well as competing models such as ChatGPT, but at a fraction of the cost. So that's got a lot of the AI players over here taking note. In fact, Mark Zuckerberg has reportedly launched a war room where he's got many of his AI employees trying to figure out how they can mimic the success of DeepSeek and, of course, the DeepSeek costs. So lots of exciting things happening in the AI world over here.
It's really quite hard to tell, isn't it, at the moment, sort of where this whole thing is going. But, you know, exciting for us, Autria. We've got Laila joining us later, so she'll be able to sort it out. We're also going to be talking to Jeff Nivala, co-director, Molecular Information Systems Lab, which is a partnership between the University of Washington and Microsoft, about his work developing methods for storing digital data in DNA.
You can start to imagine data centers of the future, a data force and these sorts of things.
Well, I'm absolutely delighted, Autria, now to be joined by Laila. Laila, welcome.
Thank you. I'm delighted to be here.
Laila, who, for those of you who don't know, is the Director of Strategy and Research at WebsEdge, which is the company behind the podcast. Now, Laila, thank goodness you're here. All right. So what's going on?
So we've got this issue with data storage where the field of data storage has lagged behind that of kind of AI innovation and technological innovation, where for the past 4 decades, we've just been making transistors smaller and smaller and smaller.
Right.
And that's resulted in kind of reasonable increases in the ability for us to store data more efficiently. But we've kind of hit a limit with that because you can't get any smaller than where we are now. So I think it's a very interesting space where I think we're going to have to think really big and innovatively and look to other domains to try and solve this problem, which hasn't really been solved by kind of engineers and computer scientists yet. And I am a little bit, I'm a bit reserved when it comes to pop science-y kind of ideas, but I think you got to think big to make it big.
I need to push you on this DeepSeek stuff. I mean, where are we? I mean, are we 50 times more efficient or not?
So I think what DeepSeek has done, obviously, is shown that you can achieve the same result using different strategies and less compute. So rather than working on a giant scale, you can kind of call to these smaller parts of the model. So I think it's shown us that we don't need as much compute, or the price of compute isn't that high, but I still don't think it takes away from the data problem and the fact that we're still going to continue to generate tons of data from everything we do, all of our technology, all of our existing technology, as well as the AI and the use of AI and the things that that's generating, as well as kind of memory. So we talk a lot about agents, and it's very hyped that we're going to have these agents, that agent. But in order for agents to function well, they need to be able to speak to what is a repository of knowledge. They need to be able to access it. So when it comes to using things like AI in cars, autonomous vehicles, and other use cases, the AI needs to be able to access information quickly, right? So the data storage problem and the data retrieval problem is still a problem. So I don't think something like DeepSeek necessarily has solved every single problem that we've ever had. There's still a long way to go, and I do think data is key to it.
Perfect. So, Autria, we are indeed going to need alternative forms of data and data storage.
Yes, I would like to ask Laila one more question, and why she thinks that DeepSeek was able to, create this AI foundation for a fraction of the cost. Do you think that it's as good AI as we're seeing for, with the $100 million companies?
I think it's great. I think the reason, and I mentioned this to Stephen earlier today as well, is that when you're constrained on resources, you're able to do amazing things. And I think it's the same premise by which OpenAI was able to leapfrog DeepMind and Google, that they have limited resources. So you're forced to innovate with the small amount of resource that you have. And I think that is just fundamental to all progress that we've ever seen in terms of technological innovation.
And so now to dig a little bit deeper is Dr. Jeff Nivala joining us, the co-director for Molecular Information Systems Lab, in a partnership between the University of Washington and Microsoft. If you're enjoying our show, please don't forget to subscribe to Agents of Tech. This really helps develop the show and shine a light on what Laila was just talking about, the cutting edge research. So thank you. It's our pleasure now to have Dr. Jeff Nivala, co-director for the Molecular Information System Lab, joining us here. This is a partnership between the University of Washington and Microsoft. Thanks for your time today.
Yeah, of course. Great to be here.
Jeff, can I kick off? Everybody's talking about data storage at the moment, data and data storage. Can you talk us through your work with synthetic DNA for data storage and why you've taken this particular path?
The rise of modern technology, sort of going through the information age right now, things like IoT, cloud services, the internet is generating tremendous amounts of data at a scale that humanity has never seen before. And so we're starting to essentially exhaust the limits of conventional storage technologies such as tape and solid state drives and these sorts of technologies. So exploring new technologies like DNA data storage is really attractive because compared to those traditional storage media, DNA is incredibly dense, so orders of magnitude more dense. You can store a lot more information in less space. And it's also incredibly durable. So when stored in the right conditions, DNA data storage can have lifetimes of many thousands to potentially millennia lifetime.
Jeff, I'd like to get your take on, the big announcements here recently, like the Stargate Project, this huge $500 billion investment into AI in the United States over the next 4 years. Your thoughts on, I guess, really the excitement of that and the basic question, how on earth do we create the storage that this type of investment might generate?
So what we do know about AI, it's incredibly powerful, but it's incredibly data hungry. As we, sort of are exhausting our limits, our ability to store data using conventional methods, being able to potentially store data much more efficiently by learning from how biology stores information, like using DNA or other molecular forms. Potentially, this would be a more sustainable approach to be able to power, what all the information storage that we're going to need for this next generation of AI technology.
So to that point, you're working obviously at the intersection of biology and computing. I think for most people, that's two fields that seem very different. What drew you to combine these areas, and what surprises have you found in trying to make biology work as a computer storage system?
Yeah, so I see biology really as a technology, sort of the original technology. And so if we look around us, all the amazing things that biology can do today, that it's evolved, over billions of years to store information, to process information. And these are all the sorts of things that we build electronic systems to be able to do as well. And so I think the more that we can learn from biology to build better computing systems, I think that's sort of the future of sustainable computing. Some surprising things that I've learned is that it can be incredibly difficult to engineer using biology to act like a computing system because, biology, like I said, has sort of evolved over billions of years to do the things that it wants to do. And when we try to make it do what we want it to do, surprising things can happen because you're sort of trying to override the inherent what it was originally programmed to do. Everything that you build with biology, it's not in a black. It's sort of in a black box, right? So it has a lot of interactions that you don't know about until you discover something is not working as behaved, or something is not behaving as designed, and you need to figure out, okay, what's going on in this system that I don't understand yet.
When we think about data storage, we don't automatically think about DNA, and we don't automatically think about biology. We think about big server racks in huge concrete buildings with air conditioning, units all around them. So I think it's really interesting the way that you said you saw biology almost as the first, technology. And I wonder, do you think that this means we need more, if you pardon the pun, cross-fertilization? We need more computer scientists and more biologists or geneticists actually working together on this.
So certainly it's that interdisciplinary nature that's going to make this technology reach its full potential. And so that's what we're trying to do with the Molecular Information Systems Lab. It's really bringing together experts in molecular biology, experts in computer architecture, programming algorithms, and it's these sorts of things that really fertilize the cross fertilization, as you said, because really no one can be a domain expert in all of these areas, right? It really takes these broad groups of backgrounds to be able to build technology for real applications.
Okay, so how does this work? How do you encode digital data in DNA? Can you boil it down for us to kind of explain the actual mechanics in terms of the process?
So it starts with taking your digital bits, right, which are traditionally represented as zeros and ones. You can essentially encode any information using binary, as it's called, right? So text, images, videos. So you can take the zeros and ones, these digital bits, and you map them into essentially sequences of A's, T's, G's, and C's. Okay, and you do that. That's called the encoding portion of it, right? So you have this mapping scheme that goes from the digital bits to DNA bases, and then you actually then synthesize or physically make these strands of DNA now. And now you actually have this digital information is now preserved within these DNA molecules that now exist physically, and those can be stored away, right? And like I said, so you can store these away under the right conditions. This information will be preserved within that DNA for a very long time, using essentially minimal energy expenditure to keep it safe. And then when you want to retrieve that information back out, you use DNA sequencing technology that essentially you put these molecules into a DNA sequencer. It'll read back the sequence of the A's, T's, and G's, and C's within those DNA strands, and then you can use software essentially that can decode those sequences back into the digital bits that represent your information, and then you've essentially gone end to end from digital bits to DNA back to digital bits again.
Jeff, I want to kind of build upon that and talk about why we're using biological infrastructure as opposed to electronic infrastructure. And this is mainly because, you obviously mentioned that DNA was kind of the first technology, but throughout history, when we've, I guess, tried to mimic biology, such as, flight, we built planes, which didn't necessarily mimic the wings of birds, but we didn't try and build muscle necessarily. So how come we've kind of gone down the route of bioutilization as opposed to biomimicry? Because, sequencing and PCR is quite laborious.
What we're really doing is sort of at the very beginnings of using biomolecules for computing. The easiest thing to do is directly borrow what nature has done, right? And so using, sort of traditional DNA-based storage, we're using traditional, sequences of DNA, molecular structures that biology has used. We're using sequencing and synthesis technologies borrowed from the life sciences. So I think that's gotten us to this stage, but there's still a lot of technical barriers to overcome to make it mainstream. And I think this is where your point comes in, as now we sort of need to think about not just directly borrowing things from nature, but how do we sort of now take it to the next level, going beyond what biology has done and building, use technology as a substrate, but now optimize it to get to that next level and be able to not compete with electronics necessarily, but complement it.
Current DNA storage is positioned as cold storage. Do you think DNA could be used as a storage which would allow for more frequently accessed data? I know I recently actually came across a paper from Peking University where they were using epigenetic methylation to kind of speed up that process. But do you have any views on that? And how we can progress from going from cold storage to more kind of dynamic storage?
Yeah, for sure. So I think to go from progress beyond cold storage to dynamic storage, we're going to have to sort of reinvent new technologies for reading and writing of DNA or potentially other molecules beyond what's been developed for the life sciences. The metrics that you might want out of a DNA sequencer to sequence a human genome might be very different than what you might want when you're trying to sequence, information that's encoded with synthetic DNA. You could deal with a higher error rate if it decreases the latency, right? The research that I'm really interested in developing is new technologies that are optimized for reading and writing biomolecules with the applications directly for computing and data storage.
I think the idea of DNA as a universal constructor in the regard that it can essentially take knowledge and turn it into matter is pretty extraordinary. And I guess on that point, do you see potential for us to build something which acts like DNA as a universal constructor in the respect that the DNA or the synthetic DNA is able to have active properties like self-replication, where it not only stores the information, but has the capacity to replicate it and build something from it?
Potentials all around us of what DNA has the capability of doing, of not just storing information, but being able to replicate it, having molecular mechanisms that encode or are able to do things like error correction as you make copies of it. So amazing things, in addition to being blueprints that can then build molecules that are much more complex than the DNA itself. So I think if you look at sort of the full stack of what exists in biology, going from storage all the way to information processing, it involves not just DNA, but things like RNA, proteins. And so I think as you're moving beyond storage and you think about more towards molecular computing, I think we're going to have to extend beyond DNA because it's relatively limited in what it's able to do. And I think things like protein engineering and protein design will allow us to do more sophisticated computing, similar to the way biology is able to do so much, sense and respond and process information in the way that it does.
Jeff, so how do you make what you're working on more scalable, and how do you make it more accessible to non-experts?
Well, a big part of it is building upon these technologies that are originally designed for life sciences. Now we sort of have to rethink the design for information storage and computing applications. And so that's how we get these potentially get these read and write more scalable. In particular, the technology that I've been developing for a long time is called nanopore technology. So it's a way to sequence DNA or other biomolecules that's incredibly portable, low cost, can plug into your laptop, even a smartphone, and be able to sequence DNA and potentially other molecules that have information stored in them. So I think going towards more ubiquitous molecular storage, nanopore technology is going to be a very promising technology going forward. And the way that we may also make it more accessible is by automation. Everything that we're doing right now is sort of in the lab and people are bumping into each other with pipettes and whatnot. Being able to have automation technology such as, microfluidic systems, digital microfluidic systems that can be miniaturized, low power, and be able to, essentially move all these droplets of water around, essentially is what we're doing, that carry all this information in an automated, compact ways is what we need to do to get to that next level.
So kind of on that point, like where things stand right now, how could other people who are maybe working in your field leverage your work in order to contribute to the field? And when do you think the average person could start using DNA-based storage?
To the first question there, how do folks getting more involved? I mean, I think what's great about this, molecular information storage and DNA-based storage and information processing is that it really, it's such a broad field that, if you have expertise or interest in biology, in particular molecular biology, you can start to get involved with it that way. Or if you're coming from the computing side, learning more about biology and how you might be inspired to build better systems with this new substrates that biology offers. There's a lot of open source sort of encoding and decoding tools that folks can play around with as far as to explore how information is practically encoded into DNA sequences. As far as when will it practically sort of everyday lives, I mean, I think for the archival storage or this cold storage, I think that's going to be within the next 5 to 10 years. I think it will be start to used at a much larger scale. There's already, startups that are commercializing the technology right now as far as using DNA for storage. Going beyond that, I think there's a ways to go to make it more practical as far as competing with traditional electronics as we think about computing. But I think computing can be really broadly defined in that there are, we can bring molecular computers into spaces and applications that traditional computing cannot do. I think for healthcare and just new mechanisms of understanding biology, molecular computing is already starting to have applications, and I think that's just going to continue to grow from there.
I do have one final question for you. Over the next 5 to 10 years, when you see this becoming much more practical and applied, do you see DNA-based storage as being one of the key solutions to the data storage dilemma?
I do. I mean, I'm sort of inspired by nature. If you just look around us, all the information that's contained in living life forms that's all around us, that's able to sustainably propagate and coexist with other life, in harmony, essentially, with life on Earth. Looking 100, 500 years from now, you can start to imagine data centers of the future, data force, and these sorts of things. And so I think that's sort of the imaginaries I like to think about. It's a long ways away, but it's what drives me.
All right, really fascinating technology. Thank you so much for your time today. This has been so interesting, and we really appreciate it.
Yep, thank you.
Well, it's not very often, is it, that you finish an interview with a picture in your mind, right? And I can't get that out of mind now with forests of data, right? So I started off today with these concrete built data centers all around the world that are just going to be, a blight on our environment. And now I've got a lovely forest in my mind for data. Wouldn't that be great?
Yeah, it feels good to look towards nature. I'm kind of with Jeff on that because like DNA, obviously it's in everything. And I feel like I'm stating the obvious, but if you actually look at it, it's just 4 letters, which can store, is so data dense in that respect, in a way that I think 1 gram of DNA can store 10 million hours of HD video.
Before we did this interview, had you ever even imagined DNA as a data storage device?
My experience of dealing with DNA is what Jeff was talking about, pipetting in a lab. You're there till 11 p.m. and it's frankly a nightmare. So no, I didn't think about it. But his point about being able to use biological computing in places which electronic computing can't be used just blew my mind.
In addition to the high demand for space in order to store all of this, there's also the ongoing conversation about sustainability and the drain that this might have on the power grid. And are we going to be able to power this? And so, I think that these are really interesting and dynamic and creative ways to try to find a solution to that problem. Really fascinating content today, but that is it for this episode. If you enjoyed our discussion today, don't forget to like and subscribe because that really helps us improve the show and curate our content. Until next time, thank you so much and goodbye.
Goodbye.
Until next time, it's goodbye.
Agents of Tech is brought to you by WebsEdge. Our special thanks to our studio engineers Adam Dean and Cody Wynn, editor Abby Harries, and our producer Kath Sheehan.